In Notes 5.3, you are going to learn how to write formulas for ionic compounds. Remember, ionic compounds are those compounds that exist because electrons have been transferred from one atom to another. This results in the formation of positively and negatively charged ions, and the attraction for those oppositely charged ions is what holds that compound together. Before we get into learning how to write formulas, we first need to talk about what are known as oxidation numbers. Oxidation numbers are the numbers that are used to indicate the charge on an ion. So remember, atoms become ions by gaining or losing electrons. The oxidation number for an atom is just the charge of that. It can be both positive or negative, and it is representative of the number of electrons lost or gained when the atom combines to form a compound. So those atoms that lose electrons to get to a full outer shell are going to have positive oxidation numbers, and those atoms that gain electrons to get a full outer shell are going to have negative oxidation numbers. There is a pattern on the periodic table to determine the oxidation numbers for various elements. So remember, our group 1 elements are the alkali metals, okay, with the exception of hydrogen. And these group 1 elements, remember, with one valence electron, want to lose that electron to get to a full outer shell. As a result, the elements in group 1, with the exception of hydrogen, have an oxidation number of +1. Okay, next to our alkali metals, we have our alkaline earth metals, group 2, and for those atoms to get to a full outer shell, they want to lose 2 electrons. So atoms in group 2 are going to have oxidation numbers of +2. Okay, the middle section of the periodic table, those B elements, are a little harder to determine, so we're going to kind of skip over those for now. We should recognize that elements in group 3 want to lose 3 electrons, and so they will have oxidation numbers of +3. Okay, group 4 can be a combination of both positive and negative, so we're not going to assign oxidation numbers to the elements in group 4. But now when we look to our nonmetal side of the periodic table, we're dealing with atoms that want to gain electrons, and so our oxidation numbers are going to shift from being positive to being negative. So on the right-hand side, in group 5, we have oxidation numbers of -3. In group 6, we have an oxidation number of -2. And in group 7, we have an oxidation number of -1. You may want to pause this video right now, take out your periodic table, and add those oxidation numbers to the top of your periodic table. They are already written on the periodic table in class, so you will always have access to that information, but those oxidation numbers are important because they help us determine the type of, or the chemical formula for a compound. Okay, notice that, again, our group 8 elements, our noble gases, do not have any oxidation numbers because they already have that full outer shell. They don't want to gain or lose any electrons. Okay, besides oxidation numbers, we also need to understand what a polyatomic ion is. A polyatomic ion, by definition, is or are tightly bound groups of atoms that behave as a unit and carry a charge. In other words, polyatomic ions are ions that are made up of more than one atom. Okay, but we treat them as just one singular substance. You were given this polyatomic ions reference sheet in class, and again, you will always have access to this sheet. So as long as you understand how it works, you don't have to memorize anything on it. But what this polyatomic ion reference sheet shows us is a list of some common polyatomic ions and what their charges are. So at the top of the sheet, we can see that there is one positively charged polyatomic ion, okay, and that is ammonium, and it has a charge of +1. Now if I look closer at this ammonium ion, ammonium is made up of nitrogen and hydrogen, right? 1 nitrogen, 4 hydrogens. So it's 2 separate elements, but we treat this entire thing as one, and that entire thing has a +1 charge. Okay? Everything in the first column here is a polyatomic ion that carries a -1 charge. In the second column, everything has a -2 charge, and in the third column, a -3 charge. On the left-hand side, you can see the name of the polyatomic ion. And then on the right-hand side, you can see what the actual formula and charge for each one of those ions is. So again, you will always have access to this. You don't have to memorize anything on it. You just have to understand how to use it. So now that we understand oxidation numbers and polyatomic ions, we're going to talk about some basic rules for writing formulas for ionic compounds. So the first thing we have to remember is that ionic compounds are electrically neutral, which means that the positive ion and the negative ion will always balance each other out. So the net charge of our compound should always equal 0. So whatever the positive and the negative charges, they have to cancel each other out so that the overall charge of the compound is 0. That's why we say it's electrically neutral. When we write chemical formulas for ionic compounds, the positive ion is the one that is always written first, followed by the negative ion, and we want to make sure we always use the smallest ratio of atoms. So what that means is, let's say I come up with a formula of Na2Cl2. Okay, these subscripts right here represent the number of atoms that are involved, but since they're both 2, they could be reduced to NaCl. So we want to always use the smallest ratio of atoms when we're writing formulas for ionic compounds. The easiest way to learn how to write chemical formulas is to just start looking at some examples. So we are going to start by writing the formula for a compound made from the combination of potassium and chlorine. So the first thing we're going to want to do is determine the element symbol for each one of these atoms and also determine the oxidation number, or the charge. Again, the oxidation numbers can be determined by the location of those atoms on the periodic table. So if I look at my periodic table, I can see that potassium has an element symbol of K, and the oxidation number is +1. Okay, on the right-hand side of the periodic table, I can see chlorine has an element symbol of Cl and has an oxidation number of -1. It's found in group 7. It wants to gain 1 electron, so the charge is -1. When I combine these, I'm going to make sure that the positive ion is written first, which is my potassium, followed by the negative ion, which is my chlorine. Remember, when we write element symbols, the first letter of the symbol is always capitalized. The second letter is not. So in chlorine, I capitalize the C, but the L needs to stay lowercase. Okay, when I combine these two, I should be able to see that potassium being +1 and chlorine meaning -1, if I add those charges together, the overall charge is 0. Oops. Okay, so if the overall charge equals 0, then I know I have a neutral compound. And so the chemical formula for the combination of potassium and chlorine is simply KCl. Okay, if we look at another example, calcium and bromide, we're going to start again by looking at the chemical symbol for calcium, which is Ca. The charge of this ion is +2. Okay, it's found in that second column, and the elements in the second column have the +2 oxidation number. If I look up bromine, bromine has a symbol of Br, and the charge of bromine is -1. Okay, when I go to combine them, calcium is first, followed by the bromine. Only this time, each calcium atom has a +2 charge, and bromine has -1. So if I add these charges together, +2 plus a -1, I get an overall charge of +1. And remember, we want our overall charge to be 0. So I'm going to change this to add another bromine. Okay, so if I add another bromine atom, I now have 2 bromines, and now my overall charge is 0. To show that in a chemical formula, I'm going to add what's known as a subscript. A subscript sits below the element symbol and indicates how many atoms of that particular atom there are. Okay, so it indicates the number of atoms in that compound. So for every 1 calcium I have, I need 2 bromines to get a neutral compound. And so the chemical formula for combination of calcium and bromine is CaBr2. Okay, the subscript for calcium is a 1, even though it's not written. Okay, so we never write subscripts of 1, but just recognize there's 1 calcium for every 2 bromines in that formula. Sometimes when we're writing formulas for compounds, the ion charges don't cancel out as easily, and so we can use something known as the crisscross method. The crisscross method says that the ion charge can be crossed over and be used as the subscript of the opposite atom. And again, this method is useful when charges don't balance out easily. So again, using the front of my periodic table, I can look up aluminum and say that aluminum has an element symbol of Al and an oxidation number of +3. I can see oxygen has an element symbol of O and an oxidation number of -2. Okay, trying to cancel out +3 and -2 to get a neutral compound can be a little tricky, and so we can use, again, this crisscross method. The crisscross method starts the same way. I'm going to list aluminum first, followed by oxygen because the aluminum is positive. But now what I'm going to do is this 3 for my aluminum is going to tell me that I need 3 oxygens. So the charge of the aluminum crosses over to tell me how many oxygens I need. And again, I write that as a subscript. The negative charge of the oxygen I'm going to ignore, but I'm going to take that 2 for my oxygen and cross it over to use as the subscript for my aluminum. So I end up with a formula of Al2O3. Okay, if I pay attention to the charges or add them up, each aluminum is +3. So +3, +3, each oxygen is -2. Okay, if I add that all together, it gives me a net charge of 0, which means this compound is neutral. The crisscross method can be used anytime, but again, it's really the easiest to use when you're dealing with charges that are +3 and -2. Okay, the last thing we're going to do is look at some additional examples where we're asked to write formulas for polyatomic ions, or for compounds that include polyatomic ions. So in my first example, I'm going to start the same way. I'm going to use the front of my periodic table to say calcium is Ca+2. Okay, now the nitrate ion is a polyatomic ion. So if I refer to my polyatomic ion reference sheet, I can see that the nitrate ion has a chemical formula of NO3. Notice it's capital N, capital O with 3. And the charge of this polyatomic ion is -1. Okay, again, I keep in mind that I want this compound to be neutral. So since nitrate is -1, I need 2 nitrates to cancel out the +2 charge of the calcium. To show that in a formula, I start with my positive, which is CaNO, and then the NO3 is negative. And now I need 2 of these NO3s to cancel out the +2 charge. What I'm going to do is I write the formula for the polyatomic ion, NO3, but then I'm going to put the whole thing in parentheses and add another subscript of 2 next to it. This 2 is saying that I have 2 of the nitrate ions, the NO3. I need 1 calcium and 2 nitrates to get a neutral compound. We can never change the formula for a polyatomic ion. We don't distribute that 2. We just leave it as the formula NO3. If we need more than 1 polyatomic ion, it goes in parentheses with the subscript outside. Okay, if we look at our second example, ammonium and phosphate. Both of these are ions, so we're going to look at that polyatomic ion reference sheet, and we're going to see that ammonium has a chemical formula of NH4 with a charge of +1. Phosphate has a chemical formula of PO4 with an overall charge of -3. Again, I need the positive and negatives to cancel out, so I'm going to need 3 ammoniums to cancel out the -3 charge of the phosphate. So my positive ion is ammonium, NH4. My negative is phosphate, PO4. I copy those polyatomic ion formulas down exactly as I see them, but to show that I need 3 ammoniums, I put it in parentheses, and I put the 3 on the outside. So NH4 in parentheses, subscript 3, followed by PO4. Okay, my last example, I'm going to look at magnesium and acetate. Magnesium is an element, so on the front of my periodic table, I can see it's Mg. The charge, or the oxidation number, is +2. Acetate is a polyatomic ion. It has a longer formula, C2H3O2. Okay, that formula stays the same, but that entire ion carries a charge of -1. Again, we should be able to recognize, to make this compound neutral, I need 2 of the acetates to cancel off the +2 charge of the magnesium. To translate that into a formula, I start with my positive ion, followed by my negative. Notice I'm not changing the formula of that polyatomic ion. To show that I need 2 of them, I put the whole ion in parentheses with a subscript of 2. Okay, polyatomic ions should only be in parentheses if you have more than 1 of them. Okay, so in my previous example with phosphate, I only needed 1 of those phosphates, so I did not need to put it into parentheses. So those are some examples in the rules for writing formulas for ionic compounds. Remember, ionic compounds are electrically neutral, so the overall charge of the compound should always be 0.